Good morning, everybody. Our first keynote address in ISRIAH 2022 will be given by Professor Hiroaki Wagatsuma on brain-inspired robotics applied to cyber-physical space issues. Let me briefly introduce Professor Wagatsuma to the audience. Professor Hiroaki Wagatsuma started his career at the NEC Corporation for producing the world's first generation of the notebook-type computer PC-98 Note, released in 1989. He received his MS in Mathematical Sciences in 1997 and Doctor of Science in Mathematical Sciences in 2005 from Tokyo Denki University. In 2000, he became a special postdoctoral researcher at RIKEN for studying computational models focusing on the brain oscillation. From 2003 to 2008, he was a research scientist in the Laboratory for Dynamics of Emergent Intelligence at the RIKEN Brain Science Institute. He was a senior research scientist. His research interests include theoretical modeling of brain oscillations, the memory integration process of experienced episodes, and the implementation of oscillatory neural networks into neurorobotics. His research for elucidating emerging process of creative decisions depending on spatial and behavioral contexts in the brain by using the robotic platform has received great interest and is supported by grants from the Japanese Ministry of Education, Culture, Sports, Science and Technology. Dr. Wagatsuma is currently professor at Kyushu Institute of Technology, QTech, in the Department of Brain Science and Engineering, Graduate School of Life Science and Systems Engineering. May I request Professor Hiroaki Wagatsuma to give his keynote address on brain-inspired robotics applied to cyber-physical space issues. Professor Wagatsuma, please.
Thank you very much for the kind introduction. So, can you allow me to share my screen? Thank you very much for the kind introduction to me. So, I would like to express my sincere gratitude and honor for the having opportunity have presentation here. I have two professors, Professor Jacques Bhattacharya, IIT Kanpur, and Professor the Ogai, the IPS at Waseda. So indeed, I have the respected the long time and the Professor Ogai, and when I come the QTech here, he provided so many the research product, and then also the influence the researcher, especially in the field of the autonomous driving. I have so many inspiration of the Professor Ogai, and in the framework the cooperation QTech and Waseda. I would like to express my respect the best regard Professor Ogai in this opportunity. So can I see this my screen? So this is my presentation. Brain-inspired robotics applied cyber-physical space issues. So I would like to start my short introduction, what kind of the project I'm doing here. So this is a challenging issue for me to call the brain-based embodied intelligence. What are the challenging issues? The first mission for us, the automatic solution generator in the dynamic environment, a very good task condition, like our brain intelligence. Second mission, productive and creative coordination mechanisms between the brain-body system and the machine, such as the artificial or augmented body person. Third point, assurance in the presentation to transfer meaning and the intention for understanding a situation by robot to cooperate with human worker. Fourth mission is very important but difficult. Unsolved mystery, the human mind and the consciousness, with the ultimate goal to elucidate our intelligence in the sense of the developmental difficulty, learning difficulty, rehabilitation, and the aging. So then our approaches using mathematics and the systematic approach to analyze this kind of issue. That's why the big question for us, can we systematically solve those issues? This is a visualization, how we treat these issues. This is a space problem. We are living in the physical world and tasks we have. That's why we need to understand what is the task or condition. Cooperation is necessary with other counterpart, machine, human. We have a body. That's why we have a risk. This is a fast plot, focusing on the space issue. Secondly, our activity has a limitation of time. We have time. When I was born, development start. Next, we need to learn something more. Development, in a sense. Then finally, we cannot avoid the fate, aging, and longevity. So then, how we can solve with our brain? We need to think, or having some emotion in some cases. That's why our brain projects this kind of information that obtained in the external world to provide internal representation. Therefore, we have intelligences. How we can solve the problem in a space-time condition. This is my mission. Therefore, we need to use mathematics in a systematic solution. We have to think about kind of state spaces. We try to simplify in the sense of the model to get solution. This is a vision, our brain-based embodied intelligence. We need to think self, body, synchronization, task, risk, disability. We try to understand the situation, then project. Depending on the condition or the space and the time, then we try to think about a kind of generalized method as a mathematical analysis to help to understand logical extraction, method to avoid potential risks, care, and disability. Therefore, we are focusing on the risks of sensitive and vulnerable aspects of the animal and the human being. This is a statement of my laboratory. So today's topic, we are thinking about cyber-physical spaces for the contribution engineering field. Interestingly, I was so surprised similar problem exists in the engineering field or actual industrial world. This is a kind of brain-body issue for me, but people are saying, oh, this is a kind of issue, cyberspace and the physical space. Yes, and indeed, in the factory, so many machines, the robots, they're working well now. Automation is possible by engineering schemes. We say this is the automating control system and utilization. Then, okay, according to the progress of the IoT devices, sensor collect data. Data collection is possible now. This data can be accumulated in a database or some recording system. People are using now cloud server to collect data. Even different the factory exists in the company, they can connect them together and get the data in a systematic way according to the such a cloud system. Then people are thinking now big data analysis by using artificial intelligence method. This is a point, data structure and infrastructure in the current trend. Those are very important and necessary in the current moment. Then people are thinking of the effective data storage and analysis. This is the first point I'm emphasizing the topic today. More concrete way, there's this example. Okay, there are so many machine components in the factory, IoT devices that connect them together, and the web of data is collected at the databases. Then people are thinking about standard representation. In the EU, they are thinking about standards with Industry 4.0. That's why some kind of data format is proposed. Then people try to collect this data. This is a scheme or semantic web or Industry 4.0 component architecture. I would like to express again the terminology called RDF. This is a kind of the data form. I would like to explain more detail later. This is the collaborated company and the Kyushu Institute Technology now in the government project, Yaska Electronic Corporation. They also, the Yaska Corporation is a bit famous company in the world, providing robot for the automation in the factory. They try to propose the kind of systematic system. Then robots are working well in the so many factory. Now people are thinking about the data issue, IoT and artificial intelligence. This is a very important point, not only the Yaskawa Electronic Corporation, but also so many similar the factory in the world. Data management should be connected, the production effectively. So this is a layer of the data. Firstly, we try to connect them together by using IoT devices. It's called physical resource layer. So many modules existing in the places. Then the reconfiguration, the learn to connect devices, the called Internet of Things. That's why network layer is very important to connect, but also recently, so many factories are using cloud system to collect data systematically to say server with some standard representation of data. This is a cloud application layer. This is possible now, very smoothly. Now we need to think about data analysis. Still human experts are seeing data, analyze, very, okay, expert method, very human-based. That's why such a terminal layer need to be replaced more automatic way by using artificial intelligence method. There are some the key points to think about this point. So 3 words suggested. First of all, to prevent smart factory. So first of all, the barrier connecting. The second word is the barrier to data utilization. Third word, a security issue. Now I'm focusing on the first issue and the second issue, especially the second issue. So this is one example. They are trying to think about what kind of data the representation is best for the standardization. Therefore, some semantic network are important to connect, to express what is happening in the factory. For example, this is a kind of the component listed, what kind of the items necessary to provide one product. Then this is backcasting. Okay, this is necessary. Oh, this is necessary, and this is necessary. This process requires two components, and then this. The scheduling or the connection, the lack of the data or missing parts are clearly the visualized about according to the network representation of the data. This is called such as the semantic web technology. That's why this is the Spark query example. Once the database asking some request, then they ask to they check the the necessary objects. Okay, this is the main node, the object, the platform, technical data, different types of data is necessary to connect. This is the scheme now and progressing in according to the industry 4.0. So back to the brain sciences. It's my original background. A similar kind of thing is happening in the brain. Okay, it's called situated cognition or temporal granularity. This is the axis, and the vertical axis that represents temporal granularity, low resolution, high resolution. Okay, you think about it. Oh, go to the work or the working office briefly to recognize what you are doing now or what you intend. This representation can be decomposed more primitive things. Oh, go to work is kind of the combination. Go out of home or drive a car, work in the office. Oh, check today's email, make a plan, something else. Go out of home is represent. Okay, lock the door, entering the parking space, blah blah blah. This is the hierarchical structure of the data or representation. Usually your brain, the process is managing inside your mind. So that's why I have focused at a long time, my hypothesis. Okay, matching process are necessary, top-down process or the bottom-up process. Okay, roboticists mainly focus on the sensor issues. What kind of the sensor data can be obtained from the external world? Robots can grab or not, something like that. This is kind of skill or the operation. It's I call this as a kind of bottom-up process. Our brain have kind of the intention. Oh, this is a plan I have to do next. Oh, this is not the right things I want to try to grab in my plan, something else. If such a the intention and the actual skill cannot match together, okay, you cannot proceed next steps. That's why brain process is usually done in a kind of matching process, such as intention and the skill operation. This is a kind of the circulation in the processes. So the current moment, I'm in the Kyushu Institute of Technology, focusing some of the mission more engineering issue, not only the brain sciences. And then so many requests come in the company, industry field, or the collaborative research missions. I face firstly, what kind of the artificial intelligence technology can be used. Then people try to focus on the deep learning, machine learning. Of course, I totally agree. This is very useful. But any of the method, the theory have the advantage and the drawbacks. In these cases, deep learning is nice if there is some big data. If there is big data, it has high reliability. But drawbacks, case by case. If data is not massive, accuracy getting worse. Offline learning or some incremental learning have the problem, some cases. Especially in the sense of the risk or accidental issue, we need to think about knowledge, because if data classification or sensor issue have some kind of limitation of the accuracy, if image processing fails once the 1,000 times, you can record again, then try to test. But some people did in the risk percentage. Car accident. The automated driving have they provide some car accident, hit the person, 1-2 person are dead, and 1,000 times the driving. People say complain and then with a very serious risks. That's why we need to think not only the such a black box AI, but also we need to seek a logical reasoning and the knowledge-based artificial intelligence technique. This is called ontology or semantic web. This is a kind of consistent, there are some consistent, the point, the industry 4.0 and the society 5.0 in Japan. This is an example. I collaborated the Professor Tamko and national government project and for automated driving. Yes, automated driving is possible by sensing and control, embedded such a control law. But we need to think about risk. We need to recognize, oh, this is a pedestrian. Oh, this is the road or cross section. Then we need to recognize a kind of the point to recognize the what is this. Therefore, this artificial intelligence needs efficient semantics. If artificial intelligences need to recognize, oh, this is a potential, this has a potential risks. Some alert it may provide the system. Okay, stop the curve. Even there is no the sensor data, you have to stop to prevent potential risks. Therefore, we need to think about the integration, not only the engineering, but also informatics. So many control schemes exist: target tracking, feedback and feed forward, model transition, model-based, match agent. But we need to think at the potential risks, even if there are no sensor signal from the external world, but may have accident in near future. For the issue, we need to think about such an optimization problem in the probabilistic way and deterministic way. Their scheme and historically the binary, fuzzy, support by the machine, the self-organizing map, Now I try to introduce ontology in the engineering world and to solve ill-posed problem by using sparse modeling too. Therefore, I would like to emphasize the power of the modeling. If too much simple model, you think about the interaction of the vehicle by using mass point model, you cannot discriminate actual case. Who is wrong? For example, this is a car is hitting. In this cases, oh, this car is wrong. In this cases, oh, this car is wrong. That's why hit or non-hit in the binary representation is not appropriate in these cases. Therefore, such a suitable modeling is very important. I would like to summarize the first part. Yes, we need data-driven method, crossing data. We say model-free approach. I try to introduce for the integration method, data model, data structure, and semantics based on the model-based approach. This is a funny history, funny story provided by Professor King. He's aiming robotic biology. He tried to think about the fully automating biomedical study by robot. Okay, yes, there are so many hypotheses. Try to, okay, that we can think. The work of the scientist is the creation of the hypothesis, testable hypothesis in the scientific world. And then if it's true, okay, this is the scientific discovery. He also mentioned about automated what kind of the element is necessary. Yes, what kind of the logical reasoning is possible. Deduction, induction, abduction. All swan are white. Daisy is a swan. Therefore, Daisy is white. This is the example deduction. This kind of the process when the inferences is possible now by computer machine by using semantic web technology. Yes. I propose the combination, data-driven the method, but also knowledge-based method. In other words, we say data-driven ontology discovery. We can think about the hypothesis. Human experts think briefly. Oh, this works well. More concretely. Then this is a hypothesis-driven thought. Then we can try to test such a scientific the point of view by physical world in the physical world. Recently, we are thinking about data spaces. If artificial intelligence technique can automatically test this, the combination, then hidden relationship can be analyzed. Then we say this is a kind of data-driven discovery. We can integrate them together. This is my point. Okay, this is the one example. This is a drug of the influencer. This is the actual mechanism of drug. Then there's some actual mechanism to increase the number of the buyers by using the action mechanism. So there are some the drugs, Zofruza or Tamiflu Lidenzer. This is a bias. is coming into the cell and go out. We can say in the hypothesis space, A has the anti-influenza function. This is a very brief representation. More concretely, A inhibits an action mechanism of the virus. More, concrete. But more concrete way, A inhibits RNA synthesis or A inhibits mRNA elongation to represent some specific focusing point to process. And then this can be connected actual experiment to test chemical substance works well to stop such a virus, the production. This is the ground design, our semantic integration framework built in my laboratory. If data is measured, data is annotated, then not only the co-occurrence, but the knowledge should be organized in a semantic way. Database, it represents with rules. Then according rules, based on the human knowledge, the different items can be connected in the meaningfully, then support some non-major data. This is the ground design we did. So this is a kind of history. What kind of databasing is progressing now? Firstly, people try to use a table. Now SQL databases, content management service, and now we are thinking of the RDF representation or ontology. Once we establish ontology, this is used as a common representation or standard data format. We are proposing task ontology to treat expert knowledge for operation or automation or the data curation. This is too much basic, but I'm just referring to the important point. This is a semantic web standard. There's different data layers. Firstly, we are using RDF representation, resource framework description. This is like a language, subject, predicate, object. This is a combination of data. Ontology web language. This is important for the representation property and set operation. Then RDF schema can provide the combination class in the sense of concept and instance of data. Then we can use rule language. This is the scheme we established, automating data operation. In the case of the robot factory, robots can think by themselves by using 3 types of ontology I propose: generalized ontology, place body, robot recognize where it is, the position, the localization, target relation, what information necessary to gather, target. Okay, this cases, robot have to grab in some specific places, and then the target, the target object have to be contained in the container. In action status, the status changes. Okay, I moved this object to this, or I already did something like that. Then 3 minimum sets they can solve. This is the automatic robot factory. This is the point. Action is delivered the combination basement knowledge, observation, knowledge from inferences. This is the one example at describing semantic web rule languages. We are saying, okay, this is the kind of combination of the conditions and then result. Then robot can think, okay, this can be connected in the RDF data format. Then, oh, this is a solution, something like that. This is the kind of the proposal and discovery for us. Robot works well according to the semantic web rule languages. It's very easy to decompose the three components: place body ontology and target relation ontology, action state ontology. Then condition 1, 2, 3 can be organized systematically: data representation types and relation and some specific condition. Then conclusion. More simply, yes, this is one example to treat the data. Data exists. This is a type of data. This is observable data. Then it belongs to the data files. If condition 1, 2, 3 is satisfied together, okay, consequences happening, and it's our automation, the result obtained. Okay, let's go to the actual demonstration of the robot.
I'm here in Sweden at Toyota, where I've been giving a lecture on the future of manufacturing, manufacturing 4.0, digital, artificial intelligence, different aspects of the future. But at the end of the day, it's all about teams of people working together in very precise ways, integrated fully with the very best of technology to do amazing things. About 80,000 of these things a year, and you can see them behind me. They're very precisely engineered, very heavy duty. You might be shocked at the sheer thickness and weight of the pieces of steel here. This is not building cars. This is building industrial machines that make other machines. So they're tough. They're built like tanks. And here behind me is a laser cutting components out of steel this big. And the laser is cutting it at around 2 or 3 centimeters every second. So here we have sheet steel that has been laser cut to produce large numbers of components. So I'm here in Sweden at.
So as you see the movie, sorry, according to the connection, you may have the fine video. This is one of the cases how factory works and the combination of robot and the human worker. This is one other example.
We released the HC20 a couple months ago from motion, so it puts it into a safety monitored stop as a person approaches. So that's technically a collaborative mode. Another one that can be used on industrial robots or collaborative robots is speed and separation monitoring. So this uses a laser scanner to detect as a person elevator standard 40 by 48 inch pallets. And we're going from 0 to 80 inches tall here. So, and this is like the full height of a pallet just from one riser. We don't need an elevator, and that cuts down on our integration costs and also speeds things up, makes it a lot safer because we don't have to worry about that elevator. So we are using some of the modes of collaboration with this. We have it hooked up for speed and separation monitoring enabled by the 2 zone scanners. And you can see one right over there. So right now I am in the robot's work.
This is the one, another example. And we are thinking about actual implementation, the collaborating Yaskawa robot. This is a prioritizing the cooperative work, the robot to robot. So current stages, the human operator have to make a program, robot instruction, one by one, very precisely. But we try to provide systematic method. Robot itself can think according to the rules. This is one demonstration in the virtual world, how robots works well without programming. This is the power of the semantic web. Okay. Logical reasoning works well in the top, and then recognize based on the generalized ontology, and robot can understand the situation, okay, action status, place body, and the target relation. This is parking demonstration. This is another example, the digital twin. Firstly, we tested this implementation in the virtual world, but it's developed the connection, the physical robot, in the sense of digital twin. Robot can think in the virtual world. Then, if there's no risk in the virtual world, robot can behave the short second. Okay, this is a kind of the mental imagination or a mental calculation in the sense of the robot intelligence. Okay, then such a cooperation possible now. Robot A thinking about the one rule, some systematic protocol, and second robot can work well cooperatively. It's all simulated in the virtual world and the connecting the physical world. Okay. This is the next example. What kind of the mental calculation happening in the robot? This is a state space of the robot. Then the ontology represent node and connection, and state transition happening inside the logical reasoning, the process. Then robot behave according to the instruction. If robot understand the mission, okay, human does not need programming anymore. This is another example, building a cube. It's a kind of famous toy or game, a Jenga, of building very systematically. Therefore, the robot knows rules and prohibition and this stuff. So this is a system design. Sorry, some of the Japanese the descriptions to remind. Okay, we are trying to think about implementation based on the robot operating system, ROS. We succeeded the implementation such as the knowledge-based system into the module, the ROS robot operating system. And then the knowledge database is established, and the SWAL rules is also embedded in the system. So then robot specification is also managed in the common data set. And this ROS module can load the knowledge-based databases, robot specification, and inference status, and connecting the control module, and then send to the robot. And human operator just send some brief instruction to the system. And then observation should refer to the control. This is again knowledge-based system, the ontology. We need to set some class, hierarchical classes as a concept. An entity, data instance should be connected. This is a status. It's going on or completed or still missing. Status represent. Target, oh, this is a container, this is a robot. Therefore, class, instance, data, three factors connecting them together in the databases. Class instance is connected in a sense. This is a kind of the box and entity. Okay. Robot is a concept, but some specific robot 1, 2, 3. If robot 1 start to pack in a container, and the status is initially is in non-completed, but is completed status. It's only happening. Target items is coming close to the robot within 0.3 meters. This kind of the task space in the knowledge is connecting them together in the knowledge databases. Then robot behave. Packing or cooperation is possible. This is a demonstration. Okay, this is a HC10 robot in Yaskawa the corporation. I have collaborated now the Yaskawa corporation. Fortunately now QTech Yaskawa tight corporation provide us one experimental room inside the Yaskawa factory, and then there's a called YTC room. And then we are cooperating in the company, the engineer and the researcher and student in this making this system. This is the virtual world, the virtual simulation, and connect them the physical robot and as a digital twin. And there's some camera, and there's some plate to plate ST10 exists, and there's conveyor. Object recognition possible by camera, and this is a very simple cases, number and color. Then planning using database ontology that can be done. This is the kind of the GUI, graphical interface for the human operator. They do no longer making the program, just provide instruction. Task instruction, it can be done here. Okay, try to, there's some two types of the priority by using color, red, green, blue is the highest priority, or number, sequential number, 1, 2, 3 is important or not. Once you set task instruction, which is the instruction is the most important, depending on such a priority level. Such an ontology data, the instruction coming, and GUI set such a condition or the basic requirement, and state machine works for. This is the ontology class embedded. Then action status and the place body and target elevation embedded. This is the ontology hierarchy is clearly defined. Then SWA rules. Rules that exist here as a kind of the production rule, and then they are connecting them together inside the system. Okay, let me show you the final demonstration. So this is a real robot now, digital twin. It's a very, any of the factory robots can use this kind of system. Then we proved. Goes ROS modules that we replace the robot specification. Then you can use our system by replacement the robot specification or knowledge base, depending on the task requirement. This is a case again. Okay, robot has a mission, the pick and place, some specific order. When you set, okay, this object here, this object here, this object here, this is the instruction. Then robot can think about what kind of motion is best for trajectory. Interestingly, this system, even you disturb the arrangement, robot can correct the wrong order. Okay, human interaction. You can see this operator modified robot sequence robot did. Then robot can react. Oh, you changed my order. That's why robot reconfigure again in the same order. This is the power of the semantic web. Okay, originally factory robot just think about the automatic implementation. Now robot very intelligent and interactive with humans. So I would like to conclude the summarize. Now people thinking about the firstly, we have the industrial revolution and the 18th century called the first industrial revolution. Now it's coming at the 20th century. It's more the industrial 2.0 is coming. Then now we are thinking about industrial the industrial 4.0 in the sense of cyber-physical systems. Not only the automation, but also connecting them together. IoT element is also developed, instrumented and interconnected and intelligent. Then later, the representation getting be the smart in the sense of the international standards. That's why so many CPS platform is provided now. So this is the final conclusion. So now the smart factory requires small quantity production, not mass production. That's why fine control is necessary. Effective standardization, in the sense of the easy data communication with other system, network communication, and the flexible database system, RDF representation, logical reasoning are necessary. Now we are saying, yes, data-driven AI, very important, I agree, but knowledge-based AI is highly important to support the data-driven AI. Then we demonstrate in the sense of the cyber-physical spaces. Thank you very much for the kind attention.
Thank you, Professor Wagatsuma.
Yes.
May I request the audience for any questions? We can have a few questions. Okay. Professor Wagatsuma, I have one question.
Yes.
You have talked about temporal granularity.
Yes.
How does the transition take place between from the top to down? Is it like a fractal system?
Ah, interesting. Yes. You're a genius. Yes, I basically agree. The complexity, the data transition, in a sense, just a moment. There are some issues. If the complexity increases, what kind of the solution, the extraction is possible? We also have a kind of difficulty because of the what kind of okay. This is a kind of the exploration or solution spaces. Okay, from the vague concept to the concrete concept. If knowledge database is enough to represent kind of data, but we need to have the fate or the diversity of the branches. That's why as you suggest, fine data representation is very important to minimize to represent event. If redundant representation is happening, such as skipping, switching, or the state space is happening, then the redundant calculation is happening. Therefore, some appropriate level of the abstraction is very important for the implementation. Is that okay for your question?
Yeah, thank you very much. Thank you, Professor Wagatsuma. Is there any other question from the audience? Okay, if not, then I will thank once again Professor Wagatsuma for a very informative talk on these brain-inspired robotic systems. And thank you. Looking forward to more active collaborations.
Thank you very much. Thank you. Yes. Thank you very much.